Hello, everyone. I figured I would show make a video showing both the law of cosines, law of sines method, as well as the components method for solving one of the homework questions, just to make sure that everyone has a good idea of how exactly they work. So this is problem number 20 from the most recent homework, which was the one about a charter boat. So a charter boat leaves port at a heading of north 60 degrees west for 12 nautical miles, and then north 25 degrees east for 15 miles. And then the question is how far and in what direction from port to current location. So we're going to show this in both of the methods so that you see how they are applied and what the potentially tricky parts are. First, I'm going to do the law of cosines method because that's the first thing that we did in class. So what I'm going to do, I'm going to first draw a pair of coordinate axes. The first motion is north 60 degrees west. And this is something I see a lot of people stumbling over at times. Anytime we're using quadrant bearing, the angle that we're given is always between the motion and the north-south line. So a north 60 degrees west is going to be 60 degrees towards the west. That's most of the way towards the west. So I'm going to draw that. That is 12 miles. And this angle here is 60 degrees. Then the second motion is north 25 degrees east. So that's more north than it is east, because 45 degrees would be halfway. So this is more north than it is east. This one should be a little bit longer. And it is 15. So it's going to look something like this. This is 15 miles. And what's important to realize is the direction here. We basically draw a new set of coordinate axes at the end of the first vector. Remember, you show these, you put an arrowheads at the end of your vectors. This vector, this angle here is the 25 degrees. The angle for the second vector to the north-south line, there's 25 degrees between it. And so then what we're going to do, let me just put that 15 over here. Then what we're going to do is we're going to draw the straight line from the original location to the end of the second vector. This is the straight line that we need. And now what we need to do is we need to use triangle laws to find that distance and find that direction. So what we're going to do is we're going to focus on this intersection over here where the first vector ends and the second vector starts. And what we need to know is we need to know the measure of this angle. And so remembering that when you've got parallel lines, you've got the alternate interior angles rule is going to come in handy. So that's the distance 12 over here. So what that means is that this part over here is 60 degrees. And since this part over here was 25, what's left after we do 180 minus 25 minus 60, what's left is 95 degrees. And so this angle here is 95 degrees. Now we have side, angle, side. We can use the law of cosines. So if I call this distance x, what I'm going to have is x squared equals 12 squared plus 15 squared minus 2 times 12 times 15 times cosine of 95 degrees. I'm going to plug that in on the calculator. Two times 12 times 15 cosine of 95. Always a good idea to make sure that your calculator is in degrees if we're doing degrees. Okay, so the answer that I get out of that is that x squared, if I've done this correctly, is 400.38. And so then if I take the square root of that, hold on, I'm going to get 20.00 or 20.01. That is the distance. And now what we need is we need a direction. And since we're using a quadrant bearing, I'm going to want to know what this angle is. And so in order to do that, I'm going to need to find out what this angle is. So for that, now I'm going to use law of sines, because now we've got all three sides in one angle. So sine of 95 is to 20.01 as sine of the angle that we don't know is to 15. Now, I paused there because I was about to say 60. 60 degrees, remember, is the entire angle here, all the way back to the north-south line. We're looking for what's the angle between the blue and the red. Having different colors can come in very handy here. So I'm going to rearrange. Sine theta equals 15 sine 95 over 20.01. Again, I'm writing 20.01, but use the whole number that's stored in the calculator. Makes it less likely that you will have round-off errors. And what I wind up with is that sine theta is 0.747. Take the inverse sine of that answer. We don't need to worry about it being an obtuse angle because we already have an obtuse angle. And so I get that theta is 48.3 degrees. And what that means is that this angle here, the one that I was really interested in, is 60 minus the 48.3, leaves me with 11.7. So what it seems like my answer is it is 20.01 miles at north 11.7 degrees west. Okay, so that is how we found the answer to this problem by using the law of cosines method. Now what I'm going to do is I'm going to open up a new page. I'm going to do the exact same problem by the components method, and hopefully we get the same answer. And if we don't get the same answer, we made a mistake somewhere. So hopefully that won't happen. So for this, we're going to break down each of the two vectors separately. Still helpful to draw the picture out. So we have our first one is over here. It was 12 miles north, 60 west. And then the second one was at 25 degrees north, 25 east, a distance of 15 miles. So what I'm going to do now is I'm going to break this into vertical component and horizontal component. And we've got ourselves a right triangle. That's the whole point of the components method. Vertical is perpendicular to horizontal, so you've got a right triangle. So I want to find the angle that's inside the triangle. So this angle here is 30 degrees. So what I'm going to do is that I'll call this AX and this AY, because the first vector, we just call it A. And what I know is that the sine of 30 is going to equal the vertical component over 12. And the cosine of 30 degrees is going to equal the horizontal component over 12. So I will just multiply those things out. And I'm going to get the AY is equal to 6 and AX is equal to 10.39. But we got to be careful. This is going westward. So that means I should put a minus sign on this. You got to be careful about the pluses and minuses. And it's basically your responsibility when you're drawing one of these diagrams to look and say, okay, things that are going to the left, things that are going down, those get a minus sign. Okay, so vector A is negative 10.39, comma 6. Now I'm going to do the same thing with the green vector. And in this case, it's going to be a little bit easier because both of these motions are positive. So that's nice. You can use whichever of the two acute angles. In this case, the 25 presents itself nicely. So sine of 25 degrees is bx over 15. And cosine of 25 degrees is by over 15. Now notice depending on which angle you're using, sometimes the sine is going to be matched up with the y component. Sometimes the sine is going to be matched up with the x component. Just be careful of that. Okay. So again, we're just going to plug these things in on our calculator. So 15 times the sine of 25 and 15 times the cosine of 25. And I wind up with that bx was 6.34 and by is 13.59. So that is vector b, 6.34 comma 13.59. And now I add these things together. And I'm going to wind up, I'm just going to use the actual calculator. So I have the full numbers as much as possible. So I'm going to wind up with negative 4.05 comma 19.59. And that is this vector. The vertical part of it is 19.59. The horizontal part is 4.05 in the negative direction. So now, how do I turn this back into a magnitude and a direction? Well, to get the hypotenuse, which is the magnitude, I'm going to use the Pythagorean theorem. So the magnitude of vector c is going to be 4.05 squared plus 19.59 squared under square root. Just give me a sec here. And that is 400.38. Good news is that's sounding familiar. It's under the square root. So when I take the square root of that, I'm going to get 20.01 miles. And then for the angle, this is the angle that I'm interested in. I know both legs of this triangle. Now, even though the vector is negative 4.05, for the purposes of this calculation, we're just going to use the positive number. We're going to consider the physical triangle. The length of this vector is 4.0. The length of this side of the triangle is 4.05. And so I'm going to say tangent of theta is opposite over adjacent. So I'm going to take a moment here, do that quotient, take the inverse tangent of that ratio. And what I get is theta is 11.7 degrees. And because it was up and to the left, that's north and a little bit west. And so my answer is 20.01 miles at north 11.7 degrees west. And conveniently enough, that's the same answer that we got in the other method. So both ways of doing this problem, we got the same answer. It's good news. Now, it's helpful to know both of these methods. First of all, if you get to practice both methods, you can see which one you prefer in general. But there are certain cases where one method may be more, maybe easier to use or maybe a shorter process. For certain problems, if your vectors that you were given in the first place are right along a cardinal direction, either up, down, left, right, north, south, east, west, if they're directly in that thing, then using the components method is going to be really easy. You don't need to exert any effort to break a vector which is directly eastbound into components. It's already done. And so that's a situation where you might want to use components. Also, if you've got 3 or more motions, then components are going to come in handy because otherwise you'd have to use the law of cosines twice. And that might start being a bit of a hassle. On the other hand, if your problem is only asking for speed, not velocity, but only asking for speed. So for instance, one of the questions on the homework number 35 you were asked to account for wind, and it said, what is the runner's speed to the nearest mile per hour? You didn't need to give the direction. And so in that case, if you're using the law of cosines method, once you got the magnitude, you could stop there. You don't need to find any of the angles. And so that's why it's helpful to know both methods, and also to know when one method or the other might be easier to use. All right. Hopefully you found this helpful, and have a good night.